Welcome to the next session in our course on using information theory to analyse complex systems. This session is part of a set of sessions regarding the information dynamics approach for analysing information processing in complex systems. In this session, the first part of that set, we're going to look at the philosophy behind examining information processing in complex systems in this way. So the first of our session outcomes then is to understand that philosophy. As well as that, in the next part of the next short video in our session, we're going to look at understanding the entropy rate as a first consideration in looking at information processing in complex systems. The primary reference for this session is the JIDT paper, appendices A2 and A3, for looking at entropy rate in particular, and you can look at the introduction as well to look at the philosophy that we're getting at there. So considering computation in complex systems or information processing, if we consider computation specifically from a computer science perspective, the primary theoretical tool used by computer scientists are Turing machines. We understand very well how to use Turing machines to study algorithms and to study what's possible and what is not possible in computation. But when it comes to complex systems, the question is, can we use Turing machines to make computation in these natural systems easy to spot or analyze? I'm not really sure that's the case. We can look at man-made computer systems like this von Neumann architecture with a CPU, a central processing unit. We can look at the RAM. We can look at the configuration on the motherboard and where the buses run. We can understand computation there fairly easy using Turing machine approaches. In natural systems like ants, the way they form trails, like the way that schools of fish form collective behaviour, like the way that fireflies synchronize their flashing, or like the way information is processed in the brain, it's not so easy to use a Turing machine to fit to those processes, to analyze them, or to even understand if they are a computation. One of the activities we consider in our related class on an introduction to complex systems is to look at these figures and consider whether there is computation taking place in each of these natural systems, whether or not it's taking place and what that computation is. And that's something that you should probably take a few minutes to reflect on yourself. In particular, consider whether the system is computing, and if you agree that it's computing, what is it computing? How is it computing that? What are the inputs, outputs, and information? And how are they manipulated? So feel free to pause the video here to think about those questions. I'll just consider one of these, taking the human brain. Basically, from my perspective, they are all computing. They are all processing information. They're all storing information in the individual components, sharing or transferring information between the components in the complex system, and modifying information. For the human brain, I would say what it is computing is the motor response to sensory inputs. It's as simple as that. It's taking in sensory inputs from eyes, from ears, from nose, and so on, and computing a response, an output in the way of muscle control and movement. How it's computing that, we know that's in the interaction in the billions of neurons in the brain there. So the inputs to that computation are the sensory inputs, the outputs of the motor responses. Information is encoded in the pattern of neural responses in the brain, and information is manipulated in the interaction between these activations and the activations they produce next. For me, that is the processing of information, the turning of information from those inputs to the outputs. And we'll talk more about that formal definition in the next few slides. First though, let's consider whether we can fit biological computation into this dominant computer science paradigm of computation, the idea of Turing machines. Do you think Do you think that we can fit those examples of biological computation we just looked at to a Turing machine description? It doesn't seem particularly straightforward. Well, what would we, or what could we look for in order to describe computation, whether it's through that paradigm or otherwise? Melanie Mitchell, in her wonderful book, Complexity: A Guided Tour, gives a short framework for how we might be able to do that. She suggests that we answer the set of questions in the first column here. We look at these systems and ask, what plays the role of information in the system? How is the information communicated and processed? How does the information acquire function or purpose or meaning? We can do this very easily for the computer science perspective of Turing machines. Without going into detail, they're a little bit out of scope for this lecture, but we know that information is encoded on a digital static tape that the machine processes. We know that information is communicated and processed in a deterministic, serial and error-free way with centralized rules that the machine is carrying out. And the information acquires functional purpose or meaning via the human designer of that system. Biological computation, in those examples we've just looked at, is very, very different. There, information in the system is encoded in analog states. For example, the headings of the fish are continuous or analog states. They're not digital static states like the tape a Turing machine would operate on. The information is encoded in patterns distributed in space and time. Thinking about the human brain, I talked about the patterns of activation of the neurons as a way of encoding the information that the brain is operating on. The information in the system is gathered via statistical sampling, and that brings us to the next question about how the information is communicated and processed. Here we have very much a decentralized approach. There is no one neuron in the brain that's in charge. It's a very much a decentralized processing of information in parallel, in local areas, with fine-grained stochastic interactions. And indeed, randomness is utilized in this parallel processing, which it is not in standard Turing machines, although you can design them with randomness in there, of course. The information in all of these systems acquires function or purpose or meaning via natural selection in all of these biological systems. We can then take these questions and we can think about them more precisely for each of those examples that we looked at on the previous slide, and I'll leave that to you as an activity. So it seems then that we need a new perspective to consider biological computation, in particular taking those questions into account. Melanie Mitchell says that for complex systems, the language of dynamical systems may be more useful than the language of computation in order to describe computation in these natural systems. That's a quote that I very much like. And so I think we can talk about intrinsic information processing in complex systems as occurring whenever a system undergoes some dynamical process, changing its initial state and inputs into some later state and outputs. This is a very inclusive view of what computation is, and for me it includes all those examples we looked at in those 5 images earlier. Let's look at an example here, thinking about information processing in the brain. We can think about the brain as starting in an initial state, where that state is represented by the activity in each area in some spatio-temporal pattern encoding that state. We can think about the brain taking sensory inputs from the environment. We can think then about the dynamical process that the brain undertakes, where those states on the neurons interact. They interact through time and across space in order to change that initial state into some later state, again described by the spatiotemporal firing pattern of the neurons, plus some outputs, here being motor outputs from the brain. So for me, this kind of inclusive definition is how I like to think about information processing in complex systems. And we can think then in more detail about what's happening in this bio or bio-inspired information processing, in particular compared to Turing machines. This is a very distributed process. There's not one central machine processing the information, not one central processing unit. This is distributed processing taking place in the interaction of the components within our complex system. It's ongoing, unlike a Turing machine which has a halt state. The information processing in a complex system just keeps going. Intrinsic computation, or what I call biological information processing, doesn't necessarily finish. So then we can think, how can we describe this in computational or informational terms? And we've already looked at some questions posed by Mitchell that we could start to think about there. We can then take that further and think about those questions dynamically, because we are talking about how the information in the system is being updated. We can talk about how information is stored, how it's transferred, and how it's modified in this transient process. In this transient process from the initial state to the final state, how it's processed between the interactions of the elements through time here. Now, those operations on information are easy to identify. In a traditional PC, we can identify information processing taking place in the CPU, information transfer on the buses, and the RAM providing memory. It's not so easy to identify these elements in a biological computation. With that said, we qualitatively talk about such operations very often in complex systems, and indeed, I think we can view distributed information processing as any process that involves these kinds of operations. We can think about information processing in the brain. We often obviously talk about memory in the brain and information transfer between different regions and processing in decision making. We can look at time evolution of cellular automata, gene regulatory networks computing cell behaviors and storing what those behaviors are, flocks computing their collective headings, and waves of information being transferred across the flock to communicate the entrance of a predator to the environment, for example. We talk about ant colonies computing the most efficient routes to food, and indeed, when we're taking this very inclusive view of information processing, the universe computing its own future. In all of these examples, the information processing is taking place during this transient from some initial to some final state. It's taking place in the interactions between the elements during that transient. And in all these cases, we tend to talk about computation as these dynamic operations on information involving memory, signaling, or processing. And you can see those terms being used for all of these examples through the description that I just gave you a minute ago. So the idea of how we want to quantify information processing, quantify the dynamics of computation, is to quantify these three operations on information, quantifying how information is stored, how it's transferred, and how it's modified. So the general idea behind the information dynamics approach that we'll look at is to quantify intrinsic operation in these natural systems in the language that the computation is normally described in this language of how information is stored, transferred, and modified. The idea being that if we can do that, we can understand better how nature computes and why it is complex. In our next short video, we'll start to be more specific about how we can quantify these different operations on information using our information dynamics approach.